So today's we will go through the second lectures on the fundamentals of modeling and control, right? So basically, before we start, okay, I just want to how to say brief you regarding the accreditations, right? As you know, okay, our program will undergo uh, another cycle of accreditations as I guess some of you already have has been selected into the the interview sessions with the panel, right? So just a brief ideas for you, right? For everyone, basically, all right? That this accreditations is an important exercise, okay? That has to be carried out by any universities, okay? That offers so-called accredited engineering degree, right? So uh, this process will take place probably every 3 to 5 or 6 years, okay? Every 3 to 5 or 6 years, okay? Depending on the number of years that being granted for the accreditations, right? During the accreditation. So these accreditations basically the panels from the we call it EAC. Okay, EAC is Engineering Accreditation Council, which the panels are professors or evaluator from other universities and one from the industry. Okay, so basically from the industry, normally they come from maybe NGOs or maybe for mechanical, usually they come from Petronas. Okay, usually they come from Petronas, right? So these panels will actually go through, okay, what have been taught, okay, to the students throughout the curriculum. Okay, so during the student interview, basically the panels only need to cross check, okay, just to cross check whether what we present to them, okay, is actually what is being delivered to the students. Okay, that's all, right? So they just want to cross check. So basically the interview sessions with the students, even we have sessions interview with the staff, uh, administration staff, even alumni and other things, just to cross-check, okay, the progress of the students and so on. Okay, so basically it's just a normal chit-chat, right? So to ensure that the process and the accreditation process of this program, okay, our program, mechanical program in UMS, to run smoothly and also to so-called to get the maximum years of accreditation, 6 years. Okay, every university they may be granted a maximum of 6 years, right? So for mechanical engineering in UMS, the accredited graduate batch will expire, okay, this year, right? So we have to apply again, okay? Actually, it's expired last year, but then because of the COVID, okay, the EAC have granted an extension of 1 year, okay, until this year, right? So hopefully, this rounds we can again achieve maybe probably 6 years, okay? So what you need to do, okay, or you may need to know, probably they ask you about what is the program outcome, right? Whether you know program outcome or not, right? Whether you know course outcome or not, okay? And also whether you have uh, check or review your progress in the program outcome or not, okay, the PO. So as you know, okay, I guess most of you have known, but if you are not know, I just a refresh ideas. Okay, what is the PO slip? Okay, so PO is the program outcome, and actually you can see, okay, your progress, okay, in terms of a slip, right? So this system you can check it out or print it out, okay, from the OBE system, okay, from your OBE system, or you can actually go through it from your handphone, the smart hardware apps, right? So I guess there is one student or PO achievement over there. Okay, so how we calculate this is basically we, instead of CGPA that you normally get, right? So this is the CGPA rating, right? Normally you get for for one course, okay, maybe for example, this course you get an A, right? So CGPA, they give you an A, right, which is equals to 4-pointer. Okay, but what we did actually in every single course, okay, the lecturer have to divide, okay, what are the assessment, maybe this test, okay, these questions is actually addressing certain PO. Okay, so we actually separate every single assessment. Okay, like your assignment, your test one, question number 1, final exam, question number 2. Okay, we key in all the marks and calculate the percentage for you. Okay, then there you can see, okay, how all these are actually being contributed to your achievement of your program outcome. Okay, your attribute, maybe the PO1 is your knowledge in mathematics. Okay, PO2 is the the analysis, right, and so on. Okay, so this is where we generate this PO slip for you, right? So once you get your grade, okay, once you get your grade in SMP, you can also actually get your PO slip or changes, okay, in this system, okay, the OBE system, or in your smart Hadir apps lah, right, basically, right? So this is the idea that you need to know, okay? And why we do this PO attainment is because we adopt the OBE system, the outcome-based system, okay? Outcome-based education system that being made compulsory for all the university, especially the engineering degree, okay, offered in Malaysia, okay, that going to be accredited, okay, because this is what we have to match, okay, the criteria set by other country, right? Because your degree will be so-called recognized, okay, by the Washington Accord countries. Okay, Washington Accords basically is an agreement between different countries. Okay, for example, US, UK in the list, German, Japan, Korea, Singapore, Malaysia, etc. Right? They have signed this agreement that all this engineering degree actually being will be recognized by their board over there as well. Okay, meaning to say, once you get this degree in Malaysia, being accredited in Malaysia, you can also actually go to other country and they recognize it as an engineer. Okay, equivalent to their country. Right, this is the purpose of doing this. So in terms in order to match all this qualification between different countries, this is where we have to show that the outcome, okay, outcome of the program itself. Okay, once you graduate, okay, the program outcome means once you graduated, okay, by the 4th year or 5th year, okay, then you have satisfied, okay, or achieved, or at least pass in all these program outcome, right? So that it is being equivalent to other countries as well, right? So this is the main purpose of doing this, right? So in the interview later on, they may just ask you regarding your understanding of why you need to do this, okay, and so on, okay. Then you have, maybe you may need to know what is the difference between the Board of Engineer, BEM, okay, as well as IEM, okay, the Institute of Engineers Malaysia. Anyone knows the difference between the BEM and IEM? Is there anyone?
No, sir.
No? Oh, all right. Okay. So if no, then I just give you a simple examples on this. Okay, this actually being quoted by I just quote this example from the chairman of IEM in Miri. Okay, sometime I think 10 years back, right? So he just mentioned that BEM and IEM. BEM is the board, right? So the board and the IEM, we call it as a learned society, okay, or community, right? So the board is the one who so-called have the authority to actually being accepted by the government to overlook this profession, okay, this engineering profession. Therefore, the board is the one who recognize you as an engineer. Okay, when you graduate, you have to register with the BEM, the Board of Engineers. right? Whereas what is the function of IEM? We call it as learned society, right? So the examples here would that I would like to quote is that if you go to learn driving, right? Driving, right? So when you want to go to learn for a car, yeah, driving license, right? So what you need to do is you do not go to the JPJ. Okay, the JPJ is equivalent like the board of engineer, right? You will get the license from JPJ, right? But you do not get the license from the Sekolah Memandu, right? When you intend to learn and get the license, driving license in Malaysia, you will go to you will look for the Sekolah Memandu, right? The driving school, okay? They will teach you how to drive, okay? How to pass all these exams, okay? So they are the one we call it learned society, okay? They will guide you and so on to bring you as so-called competence, okay, in driving, okay? Once you are competent, then only they say, okay, you can go to register with the JPJ. JPJ will recognize their so-called agreement lah. Okay, they say you have passed. Okay, so JPJ is the one who just double check. Okay, and they grant you the license. Okay, so similar to this. Okay, BM is the board who recognize your engineering degree, right? But then IEM as well as all these university lah, right? Like when you want to become an engineer, you come to university, you don't go to the board of engineer. Board of engineer only to register you as someone have the capability to perform as an engineer in Malaysia, right? They only recognize you under the act, okay? Engineers Registration Act, okay, in Malaysia, right? So this is the difference between the board of engineer and the IEM. Okay, so once you graduated, okay, you can actually register as a member of IEM. Okay, so that they may have a group of people, okay, engineers working there. Okay, they guide you and give talks and so on. Okay, so all these talks will eventually build up your credential. Okay, so that you can become a professional engineer. Again, who recognize you as a professional engineer is the board, okay? But who teach you, okay, or who guide you what step to do and so on is the IEM, right? So this is the difference between the board of engineer and IEM, the Institute of Engineers Malaysia. Is it clear?
Yes, Doctor.
All right.
Clear, Doctor.
Okay. So I think that's will end the first part, right, of the needs of the BM, the EAC, okay, the accreditation process, okay, and why you need to undergo all these things, okay. So we would say that these interview sessions, for those who are selected by the panel, it's very important for you to attend, okay, because they select it based on certain criteria, right? They may choose people from different background, okay? Maybe your entry is from Asasi, Matrix, and so on, okay? So they may want to see what is your entry requirement, okay? And whether it's match what we put in our handbook or not, okay? If we say for diploma must be 3.0 and above, okay? So they just interview you, okay? And just double check, okay? If the students say your diploma degree is only 2.5 but you get admitted, so it means something wrong with the system, okay? So they just want to cross check, okay, what we present to them is match, right? That's why they interview students, okay, the staff, okay, and everyone along the process, okay. Then yeah, that is the importance of the accreditation. So whoever selected, try to tell, if you have class, you tell the respective lecturer, especially the PBIB. I guess now you don't have the PBIB course, so should be okay. Okay, you just tell the lecturers that you have interview. They will usually let you go, right? You also have been you have received the invitation letters as well. I guess sent by today lah, right? Okay. So another items that if you notice in the Google Classroom, okay, I have put out some ebook and resources. Okay, so basically you can actually get certain ebooks or resources that are related to the course. Okay, so I have highlighted with the bracket recommended. Okay, means the content of that book is very similar. Okay, or yeah, with what we are going to learn. Okay, in this course, right? So what you need to do is just you go to UMS library. Okay, easy proxy. Okay, log in with your SMP username and password. Okay, then there you go, you have a list of maybe databases and so on, right? So you just go to the Google Classroom. I already list out from which database, okay, you can search which book and so on. All right. Okay, so back to the course, okay, for this lecture, right? So the goal of today's lectures would be to meet the course outcome number one, okay, which is the ability to model a mechanical system into corresponding transfer functions, okay, and then block diagram, which we will cover the following lecture, okay, in the following lectures, right? So in this lectures, we will try to cover from mass spring damper system, okay, 1 degree of freedoms, then follow with a 2 degree of freedoms, okay. Then we also will cover on the rotationals, okay, because in mechanical system, basically we deal with a lot of moving parts, okay, dynamic parts, and all these dynamic parts basically do two things, okay, either they translate, okay, or rotate, okay, just like a wheel and the spring and the suspensions, right? So the suspensions itself is the damper, okay, the spring, suspension, the damper, and the mass, okay, the weight of your object, right? So this will form a simplified model, okay, a very simple models that we will use, okay, from time to time, okay. I guess you have been exposed with this during differential equations probably, okay, and re-exposed again in this course, okay. Also, I guess in vibration, mechanical vibrations, right? Because it related to the movement, okay, the dynamics part, okay. So the only difference between all these courses, okay, is the approach, okay, how we approach the same mass spring damper system, okay, and how we going to analyze, okay, to obtain certain characteristic, okay, so that you can analyze them further, right? So for these courses, our main purpose is to convert this mechanical system, okay, mass spring damper system, into a form that the control engineer can understand, okay, and you can simulate it in the control software, okay, like MATLAB, okay. MATLAB, basically they have a very so-called powerful and very famous toolbox inside it, the Simulink, okay, where many control engineers actually model all those equations. They just put it then inside, and then it will simulate the response of the system. Okay, this is where or why we need to so-called follow this path. Okay, so that you have new methods, okay, to analyze it in terms of the response, okay, and finally how to control them, right? The purpose of this course, okay, to control, right? So it involves translational and rotationals, right? Okay, so again, as you know, we always say modeling, right? So this modeling words can be very wide, okay? I guess from the first years in your study, you have the course called CAD, right? CAD, you learn how to draw a model inside a software, maybe SolidWorks, okay, or in any other CAD software, right? So we call that as a model, okay? That model can be a virtual model, okay? In these courses, what we intend to model is a mathematical model, right? Mathematical equations, okay, that represent the effect of that particular system. Okay, so another kind of modeling, right? So this is what we expect in terms of modeling in the control, right? So we try to see a physical model or physical system, and then we try to capture all the respond, okay, how it will behave into a mathematical equations. Okay, we call that as model, right? And based on that mathematical equations, then from there we can further analyze it, okay, whether the system is stable, okay, not stable, and so on, right? So I guess later on you will also learn in mechanical vibrations about maybe resonance, right? Okay, I guess, yeah, resonance, you have heard these terms, okay, in the physics in SPM, right? So resonance, what are resonance, and how we actually see, okay, resonance, okay, in so-called the mathematical form, right? So from there we try to avoid all this problem, okay, so that the system will not become unstable. Okay, so this is our purpose, okay, of converting the physical model into a mathematical model, right? In many cases, okay, in many cases, we are dealing with the non-linear models, okay? However, as an engineer, we always try to simplify, all right? And we try to, even though it's non-linear, we try to linearize it, okay? So that the system become easier to solve, okay? So our purpose is very direct, okay? As an engineer, we try to see a problem, okay? It can be very big, complex problem, and we try to simplify it, okay? By breaking down them into smaller parts, right? Into a, a range of user-defined range, right? So here is your task as an engineer to find the balance between the simplicity, okay, and the accuracy, okay. The much, if it is a very complex problem and you just simplify it as simple as possible, then you may lose certain accuracy, okay. So you have to find the balance between them, okay, whether the accuracy is more important or it can be acceptable, okay, at certain level. If you further simplify and the accuracy will drop drastically too far away from the real situation, then it may not suitable, right? Actually, if you recall the weight, okay, the formula, Newton's second law, F equals to ma, right, is a simplified versions of mathematical model, okay. The more accurate one, you have to deal with the Einstein equations, okay, gravitational equations, which involve the relativity of two different masses and so on, right? So there is where the simplicity of the F equals to ma is well being accepted, okay, in the defined environment, work very well in the surface, near the surface of the earth, okay. F equals to ma, so from there you can know the weight of a mass is equals to yeah, the weight of the mass is equals to m multiplied by the gravitational force. We again use a constant 9.81, okay, or 10, okay. So this is a simplifications examples, okay. But if you are going to launch a rocket, okay, and send certain things to the moon, to Mars, okay, then this simplifications model will not work anymore, okay. So this is where you have to find the balance between them, okay, when or where to use, okay, what are the limitation of all these equations and so on, right? So here is a linear approximation of a physical model or physical system that should satisfy two properties. One is superpositions and the second one is homogeneity, all right? So superpositions refer to something like this, okay? You can not superimpose or add them up together, okay? The effect is not adding up, simply adding up, right? So here, if it is a a power of 2 and so on, then the effect is not simply adding up, they multiplies. Okay, so therefore these equations may not satisfy the superposition property. Okay, then the second one will be the homogeneity. Homogeneity refers to a property, equations or terms, okay, where you can just multiply. Okay, you have the mx terms, right? Then everything is similar. Okay, you have the mx, maybe mx1 plus mx2, mx3, and mso, right, and so on. Okay, you do not have suddenly a different terms in between. Okay, so that it become not so-called not homogeneity, right? Homogeneous. Okay, so this is a general definitions in mathematics, right? So I guess this one not really important for you now, okay? But when you start to maybe in the advanced courses, okay, where you start to see the limitations of all those equations that you derive, okay, and so on, then you will see that certain equations that you model out, okay, may not be correct, okay, because of these linear approximations that do not satisfy these parameters and so on, right? So this is just an exposures for you. Okay, here is a way of a general way of how we describe a dynamic behavior, right? So you learn from dynamic courses, okay, very simple, simplified physical system, okay. Then what you do, you draw free body diagram, okay. After you draw free body diagram, then you slowly convert them into differential equations, right? Which you again learn in probably differential equations, okay. And these courses will now start to apply, okay. From these differential equations, you have to convert them into a block diagram, okay, or so-called a transfer functions. So these equations in the block is a transfer functions, okay. They only tells you the relationship between the input and output, okay, through these equations, okay. We don't see a complex equations anymore, okay, only a diagram, right? So that you can easily visualize the whole picture of maybe a complex system, okay. So you may have one simplified physical system, okay, and or more than that, okay, maybe 10 of them, okay, and how they are interact in between them, so you can just draw an overall block diagrams later on, okay, to interconnect them, okay, the effect of all these interconnected, okay, and see what is the response when you put this input and what would be the expected outcome of the system, right? So this is the idea behind it, okay. So it looks very complex, okay, but the fundamentals is very straightforward. All right, so this is our purpose, the exposures or the fundamentals of these courses. All right, again, this is another examples or ideas of what we call linearizations of dynamic system. Okay, you may have a linear system, okay, which you have y t, okay, this referring to a functions, okay, respect to time, meaning to say you have something changing respect to time, okay. When 1 second, okay, this is the value, okay, 2 second another value, right? Then same thing with the x, okay, again x is also changing with time, right? But then this x is actually affecting the whole functions of y, okay, in the form of function of g, right? So this is how it may looks simple, but may not be so-called easy to visualize, okay, unless you get familiar with so-called yeah, playing around with the mathematics, okay, what is actually inside them, right? So internally inside them you can further depends on the equation of g, the function of gx, right? But then if we when we take into the linearization of the dynamic system, okay, we can always use a Taylor series expansions, okay. We know that this is the equations, and if we take the Taylor series, we will have a series of terms, okay, from this first term, second term, third term, fourth term until infinity term, right? But when we are talking about linearizations of the dynamic system, basically we only look at the linear part, okay? Linear part, these two particular terms, okay? The remaining, okay, the second order, third order, and infinity order, we ignore, okay? Because we usually say that the values or the effect is not big, okay, for this remaining terms, okay? So this is where we so-called linearize them, okay, into a linear form, okay? So if you see that a G and maybe an X over here, right? So you eventually form something like this, okay? It's just a Y equals to Y naught plus mx, right? So this is a linear equations form, right? So and this is very good approximation for a small range of x. Okay, so this is how we linearize it. Okay, so in other words, okay, or in the graphical form, okay, so you may see that this is the oscillations respond, right? It keep oscillating, but what we try to linearize it, we try to look at a certain range only, okay? So you can see that if you define this particular range of working region, okay, if you only want to know what is the response of theta, okay, within this small range, okay, not more than 90 degree, okay, maybe let's say this is 30 degree to minus 30 degree. It is very well defined, okay, just like a straight line. Okay, this is how we linearize the system, okay? Instead of sinusoidal complex response, we linearize it with a straight line, okay? This is the idea behind it, right? So here is an examples, okay, capture from the textbook, okay, by I forgot, Nick, I guess, yeah. Okay, so what you need, I guess, you can download it from some of the mathematical background slides, okay, from the Google Classroom, all right? So you just go through it, okay? It's just a refreshment of a technique used in differential equations, okay? How to transform it into Laplace transform, okay? So you can see that differential equations, you can actually solve them, okay? You can see that differential equation, you solve them into this, okay? So that you know what is the y, okay, respect to time, okay? And how we going to solve this is through Laplace transform, okay? One of the method, okay? I know what you learn in differential equations, you may have different methods as well, okay? You may learn the so-called conventional methods, okay, which you do not use the Laplace transform, right? But then in control engineering, we rely a lot of Laplace transform methods, okay? So therefore, it is recommended for you to just quickly go through, okay, how actually they turn it into the Laplace terms, okay, in order for you to solve into this, okay? Just changing the so-called domain, okay, from from time, okay, because your equation is all about time, right? Variable respect to time, you change the domain into the Laplace domain, okay, which is the S, okay, so-called imaginary domain, okay, and then once you change into that domain, you can solve it, right, using the so-called Laplace transform formulations, and eventually you can reconvert back from S domain into T domain. That is the idea behind this Laplace transform, right? Just quickly go through it, okay, on your own, right? Okay, so back to the main business now, right? So our purpose to model the mechanical system, and it starts from the transfer functions, okay? As you know, in the first lecture, we talked about the transfer functions, okay, which represented by the block diagram, okay, inside the block diagram, and this block diagram carries this not in equation, a functions or a terms, okay, that describe the ratio of the Laplace transform output, okay, output at the top, okay, divided by the input at the bottom, okay, the ratio between these two, so that when this input multiplied by this transfer function, it will give you the output. Okay, so this is the so-called mathematical form. They sense it, they make it being visualized, okay, by block, right? So mathematical functions convert into now a diagram, right? So this is the idea behind it, right? So you can see that the block diagram carries the transfer functions, okay, the TF over here, okay, and the relationship for this output is the input multiplied by the transfer function, okay, because the input is at the bottom, right? So input multiplied by input cancel out, you get the output. That's all, right? Very straightforward. Okay. Another terms that I would like to just get your attentions would be sometimes, okay, when you read through text online or textbook and so on, they may also come to a terms called time invariance. Okay, time invariance, basically you can quickly get a definition from Wikipedia. It refers to a time dependent functions, okay, but it is not directly, it is not a direct function of time. Okay, so you say time dependence but not a direct function of time. What does it means? Okay, so just look back at this. Okay, look back at this. All right, so you can see that the function itself, okay, is not directly depending with time. Okay, you don't multiply by time all the time, right? Okay, but you can see that there is a function over here, ut. Okay, instead of directly multiply by time, you have a functions over there, okay, ut, such that it is not directly related with the time, but indirectly related with time, such that maybe y equals to 1 second, this referring to the 1 seconds, okay, 2 second, it referring to the 2 second. Why we would define it in this way? Because you have to visualize in a way that this input in real life, it may not be straight line, okay, it can be in a form like this, okay, something like this, okay. So at time 1 second, okay, the ut may be 1, okay, at time 2 second, the ut can be 2, okay, coincidentally, okay, but at time 3 second, the ut may be 4, right? So it is not directly proportional with time, okay, so-called they are time dependent but not directly as a function of time, okay, that is what it means, okay. So I hope you get that particular ideas or meaning, right? So in the control system, okay, as we know, we will form in the form of output and input, okay. In order for us to analyze them, okay, we will start to do some testing later on, okay. All this testing, we would use a conventional or very standard test waveform, okay. So it can be in the form of impulse, okay, we just put a signal of it, okay, impulse, right, or step, okay, meaning to say it will change and forever be there. One step test input, okay, or ramp, it will continues to change, okay, and parabola and sinusoidal form of input, okay. Why or how they are related with the mechanical system, okay. Again, if you recall back the spring mass system of a car, right, or a wheel, okay, let's say a wheel, right, so you have a spring, okay, sorry, a spring and a wheel, okay. So eventually, if you form this into a block diagram, okay, or transfer functions, okay, so what would happen if this car, right, driving, and then they come into a pothole, right? So meaning to say this car now, sorry, okay, a pothole like this, okay? So the car will move, okay, and then go down and up, okay? So the changes of displacement, okay, it can be in the form of x, okay? So this form of changes can be represented by the impulse, okay, because it's just one point, change and go back, right? Then another type of form, okay, related to step is that if the road is like this, okay, suddenly like this, okay, a stairs, okay, meaning to say you drive a motorbike, okay, then this is an original X positions. So you drive your motorbike, okay, and then go down the stairs, okay, so it becomes like this, a step, right? A step or a stairs form, right? So you will drop and like this, okay? So we will use all this form so that we can see how this spring mass system will react, okay? Maybe I change a little bit of color first. What it means is that the view system will go into the pothole being given by this so-called input, okay? But what happened is that this view or this car, right? So after it go through this, okay, then it will start to bounce, okay, because you have a spring and the suspension, right? Okay, and this is what we want to see, okay, how it will vibrates, okay, or yeah, it will respond, okay, after going through this type of input, okay, similar to this, okay, your originally it can be very stable, right? But then once it go into a new step, okay, what happens is that the spring and the mass will start to being compressed, okay, and then it will start to oscillate, okay. So this is where we would like to analyze, okay, using the control system and see whether it will get damped or not, okay, being stable later on, or it will, after it go through, then your car become more shakier, okay. So this is the purpose of doing all this analysis, right? And if it doesn't being damped out, meaning to say it become unstable, okay, then you will enjoy a roller coaster until your car broken, right? So this is the purpose of doing all these things, right? So here you can again see that the transfer functions, if it is being known, then the output can be studied, right? If you know the transfer functions, you know the relationship between the spring mass or the mechanical system itself, then you can study the output, okay, how it will respond, okay, when you do a testing using a certain input, okay. Or in another way, if you do not know the transfer function, meaning to say you cannot model it mechanically, right? Okay, it's like a black box now, right? So what you can do is, normally in industry, they will form experiments, okay? They will do some testing to capture the behavior of this input and the output, okay? Instead of studying the whole system, they just study how it will respond after that, okay? And capture this into equations, and from there they can continue to simulate, okay, under different conditions, what will happen, okay? Here is examples of transfer functions. As I've mentioned, it comes from differential equations and being converted into Laplace transform, right? So here, if you have these differential equations, okay, how you can do is that in the slide itself, okay, the mathematical background slides or any textbook or online, okay, you can search on the Laplace transform form of maybe KF and so on, okay, you can search it. So you just need to check terms by terms. All right. So if this is you can see ct over dt, right? So this is the first derivative term. So what you need to do is you check with this, right? So this is Laplace transform of, no, is it? No, yeah, no. This is the df over dt. So your f is the ct here, right? So it will form an sf over here. So you have sf, okay? Since this is f, you put capital F, right? Since this is c, you put capital C, okay? So you have sc over here, right? You have converted the first term. On the second term now, you do use this one, right? Is it this one or this one? I guess this one, right? Because you have seen this k terms over here as a constant, okay? The 2, okay? The f is your function, right? So again, you will get kf. So k remain 2, okay? The f would now become c into capital C with a domain of s. Okay, repeat it to this, right? So why I would like to put these tables together to confuse you, okay? So that you will learn from that, okay? Why you do not use this, okay? Is this similar term, right? You have u bracket t, okay? This is r bracket t, right? U bracket t, r bracket t, same, all right? And if u t, you should get 1 over s directly, okay? Why you are not using 1 over s directly over here, okay? So this is the table, something similar to the test form, right? The testing input, okay? So when you do this Laplace transform, you are referring to this, okay? Transferring all these different terms into the related Laplace transform format, okay? You refer to this table, okay? However, when you come to the testing part, okay? Testing part now comes in, right? So you can see that after you form this Laplace transform form, you just rearrange them so that you form the relationship between the output and the input, right? So here we would say that the CS is the output and the RS is the input, let's say, right? So you would put in this way, rearrange, so you get 1 over S plus 2, okay? And this equals to the GS, all right? So from this form of transfer functions, now comes into a picture like the question may ask you, find the response, okay, to the input, okay, where the input, the R itself, is a step unit, okay? So when we say it is a step unit, okay, which contain this format or terms called U bracket T, okay? So immediately this refer to a step unit, okay? So what you need to do now is you would use this, okay, the step unit or the step input, okay, and the form is 1 over S, okay? Now you substitute 1 over S into your RS, okay? So you will take the RS as 1 over S, okay? If they would like to have a RAM input, okay, keep changing RAM input, so the test transfer function will be 1 over S2, okay? So you put in 1 over S2, okay, to replace the RS, okay? And yeah, you just do the mathematical, the remaining is mathematical formulations, okay? Do mathematical minus, multiply, partial fractions, and so on, okay? And eventually you will get this, all right? So pay attention, 2 things you may need to pay attention, okay, when you relearn the mathematical background. First is to know how to form this, okay, from differential equations to the Laplace transform. The second one would be to do the partial fraction, okay? Once you can do the partial fractions, then from these terms again, you recheck, okay? You recheck from this table. Now from this, convert it back, okay? Able to convert from the Laplace transform back to the original, okay? But you must go through the partial fractions, okay, in order to do that, right? So two things you may have to relearn again, right? Just to refresh, okay? So that would helps you, okay, in the remaining of these courses, right? So next one, after we know the ideas behind the so-called transfer functions, okay, now we start to do the translational modeling, right? So the first one would be the very straightforward translational, mass, spring, damper, okay? And basically later on you will make use of this, okay, later on, right? So basically you have a spring being represented by these few component or symbols, right? And you have this force velocity relationship and so on. This table you may refer it later on, right? So the idea is that I guess you have seen this before, okay? In differential equations, again, spring mass system, 1 degree of freedom, okay? So during equilibrium, okay, what we do is before we start, form into a free body diagram. So imagine that this system is hanging in the air, okay, in the cloud or whatever it is, okay. Cut them off and replace all the cutting, okay. For example, you cut through the spring, you replace it with a force, okay. You cut through the damper, you also replace it with a force, okay. And then what happens is that this object is a mass and you can convert it into another form of forces which is equivalent to the weight, right? Okay, so during equilibrium the weight itself must be equals to the force, okay, being given by these two components, okay, must be equals, right? So that's why during equilibrium we can write that this minus this equals to 0, okay. But then if now this mass start to move, okay, meaning to say we give a force, okay, to push it downwards, okay, and after you push it, maybe we release it or maybe we keep pushing at a certain frequency, okay. That's why we would put this f external bracket t as a function, okay. It can be one time, you just press one time, release, okay. It's kind of like your test input, okay. Or you can keep swinging it, okay, in a sinusoidal format and so on, okay, form. So for this derivation purpose, okay, we just put f external, okay, and we connect all the relevance of forces, okay. So mass, you have weight, okay, you have the spring represented by the kx, okay, we have also the damper represented by the fx prime, okay. Remember, for damper you have to use fx prime, okay. And also since initial conditions, we have the kx bracket when time equals to 0 as well, right? So we just total them up together since this is a free body diagram, okay. Total them up together. When in motions, we apply second Newton's law where all the forces equals to the ma, right? Summation of force equals to ma, okay. So the m is m, the a is the acceleration, which is the x double prime, okay. So summation of forces over here is taking downwards as positive, so we have f external positive or plus, okay, mg plus, okay, the remaining is minus minus minus, okay. And what I try to highlight here is the red color, okay. This red color come from this, right? mg minus kx naught, okay, and these two terms equals to 0, right? So eventually we can cancel out these two terms, and this is our equations of motions, right? So a conventional equation of motions for a spring mass system is mx double prime plus fx prime plus kx equals to the external forces. Okay, so after you rearrange, you should see this form. Okay, second order differential equations form, right? So once we see that, okay, what we need to do is rearrange again. Okay, take into the Laplace transform form. Okay, convert them into Laplace transform. Okay, the m remain, f remain, k remain. Okay, the terms that need to be transformed, okay, is the variable. Okay, so transform it into this, and this. Okay, so after you transform, we combine them together, right? So that the x is the output, okay, the f is so-called the input, right? Remember I say we would want to control the external force, okay, how it would react, right? So by solving that or rearrange them, so you can put that output, the x, how it changed according to time, okay, divide by the input. The input is our force, okay? So you form these transfer functions, okay, after you rearrange it, right? So once you can do this, meaning to say you can put into the so-called block diagram, right? And now come to the table again, right? That I've shown you previously, okay? So what happened is that you can see that these equations, okay? Yeah, these equations, okay? These equations is these equations, right? Okay. So another way to quickly use all this concept, okay, or idea, because every time you derive, okay, you go through all these things, okay, after many years, okay, people come with a simplified version, okay, because you can skip, okay, of all these ideas, okay, instead of taking the real forces over here, we now try to take or use the impedance, okay, impedance, okay, to represent the, instead of force, okay, we just directly put in the impedance value over there, okay. The spring, we just put K, okay. For the damper, we just put Fs, okay. For the mass, okay, we put ms square, okay. So why we put the ms square over here in the reverse form, okay? Mg is going downwards, okay? But here we put the mass is reverse form is because we take into the consideration that the mass is inertia, okay? It's a mass, okay? Where when we use the Newton first law, okay? Meaning to say a mass will remain over there, okay, unless you force it to change, okay. If you force it to change, if you start to resist changes, okay, the inertia of it, okay, so this mass represent the inertia, okay, that against the movement, okay, at the initial stage, okay. So if the object going downwards, the mass inertia will actually prevent or do not want to move, okay, at the beginning. So therefore, we would put in a reverse way, okay, for the mass, okay, in the impedance form, okay. So once you form these things, okay, the force, okay, that represent the external force, we just put in Fx, okay. So eventually, we have so-called directly, okay, instead of using the Fx mg, the force in terms of x, okay. Now we use the impedance term directly, we just sum them up, okay, take the summations of all of this, okay. So eventually you have ms plus k plus fv, okay, and all this multiplied by the x, okay, because the variable is x, okay, equals to the opposite side, okay, the fs, right? So you form the exact equations like the previous one, okay. So you skip all the hassle of deriving, okay. So this is another way, okay, but I recommend you to go through the first one first, okay, know what is happening, then you try the second methods, okay, using the impedance methods, okay. So from here you should get the same equations, okay. So once you can do for 1 degree of freedom. Okay, now we try second degree of freedom. Oh, yeah. What is mx double prime? Okay, double prime meaning to say second derivative. Let's this is double prime. Okay, Abdurrahman, can you see this? Okay, so this basically you can simplify. Okay, simplify in a form like this. Okay, plus 12 differentiations. Okay, y prime. Okay, sorry, plus 32 y. Okay, so this is how you get the double prime, single prime, and so on. Right? So basically, it's a differentiation.
Uh,
Yeah.
Doctor, I want to ask, you go to
Yes.
the degree of freedom one. I want to ask there, double prime.
Yes.
Next, yeah, this one here. See,
Yes.
if you say this is second one is equilibrium diagram and second one, if during motion, it mean dynamic diagram. If we say normally, this one
Yes.
dynamic
Yeah.
diagram.
This one is movement.
Here, yeah, here I can understand this K force from downward going up and upward force going down. I understand this, but this showing mx prime, what is representing this actually totally?
This one.
Mx double, yeah, this one.
Okay. This one. Remember Newton's second law. We say summations of force
Mm-hmm.
equals to ma. Right.
Yeah.
This
Okay.
a is basically x double prime.
Oh, okay. Okay.
Okay. So
Okay.
this terms is actually this graphically represented by this. All right. The directions of the aspiration of the mass. All right.
Okay. Okay, doctor.
All right. Once that is clear, then probably the second degree of freedoms is quite similar. Okay. So what is the difference is that you have to break them into two free body diagram. Okay. Two free body diagram. All right. So take one at a time, right? So we start with the M1. So you have M1, okay. Once you cut through it, the free body diagram, okay, you have to represent it. Now we are using the impedance methods, okay. When you cut through the spring K1, so K1 X1, right? Okay, cut through the damper over here, FV3. So we have FV3 S X1, right? So for damper, remember you have to put S X, okay? S X because it's a first derivative, right? So you have to put S X S, right? And then cut through this K2 over here, we have also K2 over here. So what you can see is that when you cut through this term, this component and this component, all these three components, if we assume going to the right hand side is positive, okay, going to the right hand side is positive, so all these three components will actually against this movement. Okay, initially they will pull you back. Okay, the spring, when it's connected, you push it, okay, this spring actually pull you back, right? So therefore the directions of the force, okay, is going to the left hand side. Okay, same thing for the damper. Okay, it will against you to move faster to the right hand side. Okay, same thing for the spring. Okay, so all the directions is going to the left hand side against the motion directions. Okay, that you assume. Okay, remember you have to start assuming, okay, at the beginning where is the positive directions. Okay, and you assume that is the directions of the motion at the beginning, right, in order for you to derive, right? So you know that it is going against the directions of the motions. What happened is let's see, V3 SV1. Where is SV1? Okay. Another one would be the SV1. Okay, so what happened is that this is a ground and there is a friction. Okay, and this friction actually act like a damper, right? So the faster it move, then the effect will change, right? Therefore, the ground itself, they will act like a damper as well. So you will represent the frictional force and the damper, okay, as this, okay, against the motions again, right? Then after all these things comes into the picture, the next thing that you may need to consider would be the weight, okay, or the inertia, right? Inertia. Okay. So this inertia, again, as I told you, it will delay the movement of the mass, okay, to the desired directions, okay? So you will put the ms square x, okay? So have to be careful now, okay? Is that in the form of numbering, okay? This is the block number 1, we would use x1, okay? So all are related to x1, okay? Because this is referring to the movement of block number 1, x1, right? What is the things that are actually moving to the right hand side is only the force, okay? Here, where is the force comes into picture? You can see here. This is the external force being applied to the block itself, right? So therefore, you have a Fs, the external force to the right hand side. The rest will against all the movement to the right hand side, okay, for the block number 1, okay? So this is the description why or how we come out with all this impedance, right? So once you get that one, then easier for you to actually form, right? So you will get this, okay? Then second thing that you may need to do is to check, okay, this part, all right? So what is this part now? Okay, so this part is referring to this, okay? Again, mass number 1, same mass number 1, but what is the difference is that mass number 1 doesn't move, okay? Mass number 1 is fixed, but mass number 2 is moving, okay? Now you have to imagine that M1 doesn't move, but M2 is moving. So what is the effect of M2 on M1? Okay, again, we only look into the free body diagram of this, okay? Even though M2 is moving, you only see M1, right? So what happens is that when M2 is moving to the right-hand side, they are connected through the damper as well as the spring. So whenever you have a spring connected, M2 is pulling to the right. So what happens is that this connection will now start to move to the right hand side as well. So that would be being represented by K2, but now M2 is moving. So it's X2 movement. Okay, no longer X1. Okay, even though we are looking at the free body diagram on M1. Okay, then on the damper side, similar things, okay, because they are connected, okay, the suspension itself, whenever M2 is moving to the right, it's actually pulling the block M1 to the right hand side as well, okay, which is being represented by this, okay, the damper impedance, okay, but the movement is due to the block M2, right? So when we come or consider both of the effect together, when M1 is moving, M2 is not moving, and M2 is moving but M1 is not moving, therefore we can combine them together, or we call it superpositions them together, okay? You just bring all this arrow over here, this arrow over here, okay? Okay, therefore I say the numbering is very important, right? So this is 2, this is 1. Sorry, this is 2, and the other side is the 1, right? So when you combine them together, you will see that this is the final superposition free body diagram, okay, with all the impedance, okay? So once you have this, what you need to do is straightforward, okay? Just total them up together, okay, equals to 0, right? So total up together, so F2 is positive, okay? These two things should be positive on one side of the equation, but when you bring it to the other side of the equation, it becomes negative. So you can see that minus K2 x2, okay, minus K2 x2, and also minus FV3. I guess this should be FV3, right? So, yeah. Yeah, I think this should be FV3, okay? You just double check again, okay? Probably the numbering is, there is a mistake with this numbering over here, okay? So FV3, X2, okay? So again, minus, okay? Because when you bring it all onto the right-hand side of the equation, it becomes positive, right? Then the remaining is the negative part. Bring to the left-hand side, everything become positive, okay? So everything become positive. So you form the final equations, right? So here, the questions come is, can we obtain the transfer functions that describe the relationship between the input, the Fs, and the output, X2? Is it possible? Yes, right? Okay, so how we can do that? Okay, first we have to identify the output, which is X2, and the input, which is the Fs. Okay, so output and input. Okay, so from this equation, you can already see the output and the input. The input and the output over here, right? So the only difference is that there is still an x1 over there. Okay, so there's still an x1 over there. So what you need to do to throw away the x1 is to now repeat the same methods, but now on the M2. Okay, so this diagram, now you only draw a free body diagram on M2 using two sequence. One is M2 is moving, M1 not moving, and M2 is not moving, M1 is moving. Okay, repeat the same methods. Okay, superposition them together. Okay, superposition them together, you would get this impedance diagram, right? So from there, you would have another equations. Okay, so now with this first equation and the second equations, now is it possible for you to combine them together? I guess now you can see a clearer one, right? So you have x1, x2, okay, and the output, right? So what you need to do is to remove this x1, you may use equation number 2, okay, or equation B, okay. Substitute equation number 2 into equation number 1, okay, over here. So eventually we arrange, so this term will now become a very long terms, okay, but in the form of x2. Okay, we just substitute into this, all right? So from there, now you have sufficient parameters or informations, okay, to form this x2 and over x. Okay, so you just have to try this. Okay, so I will not go in detail so that you can try. All right, so just follow all the steps over here, okay, and see whether you get something similar or not. Right, sometimes my notation is also incorrect because I'm typing all this numbering. Sometimes there is mistake over there. Okay, you just check. Okay, and eventually you should get the answer, right? So what you need to do next would be you combine them together. Okay, either you substitute or you use another method. We call it as a Cramer rules. Okay, Cramer rules. Okay. If you don't like Cramer rules, you just do as what I say, rearrange the equation, substitute it on your own. Okay, if you want to build a program, okay, meaning to say you would like to make them programmable in the future, then you may need to form into a matrix, okay, where the computer can actually calculate based on it, right? So we call it as a Cramer rules, okay, where this Cramer rules would what it does, we would use this so-called determinant of y, okay, divide by the determinants, okay. So what it means by determinant of y over here is that we would like to get the second term, right, the x2, okay, x2 term over here, okay. So what we need is to use determinant of y, okay. Determinant of y, you look at this matrix, okay, related to the y column, okay, which is this column, related to the y column, because this multiplied by x1, this multiplied by x2, right? So related to the the x2 column, sorry, okay. Then you just put this over here, okay. So eventually you form this determinant of y, okay. So you can see that this term remain, this term you replace with this, okay. So what you need to do to find determinant, this multiply by this minus this multiply by this, okay. So you get this value, okay. The determinant of the whole equations would be this multiplied by this plus minus this multiplied by this, okay. So you get the answer, right? So you have these two multiplied by this parameter, you form the so-called transfer function that you need, okay. So it's very tedious, okay, but you can see that the step is there, okay, so that you can eventually program it, okay. The step is there so that you know the computer will know which one to replace, okay. They don't need to use human intelligence to identify how to change the equation from left to right and so on to substitute, okay. So this is where the Cramer rules plays important, okay, in solving equations using matrix form, right? So I guess we should stop over here because it's already more than an hour, right? So we stop over here and we will continue again tomorrow, okay? Tomorrow class would be at 2 p.m., right? Okay, so see you tomorrow, okay, everyone?
Thank you, Doctor.
Thank you, Doctor.
All right, so see you again.
Thank you, Doctor.
Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Welcome.